Today's lesson is continuing Chapter 7, 7.3, Improving Triangle Similar. And today we have three main objectives. By the end of class, you will be able to use the three similarity rules to prove if triangles are similar or not, and if they are, use it to write a similarity statement. And those three rules that we're going to learn today and be able to use are angle-angle similarity, side-angle-side similarity, and side-side-side similarity. All right, before we get started, however, let's do a quick review of exactly what similarity means. Similarity means that if images are similar, it means that they must be proportional. So let's start out with an image of a cow here. And I can take this cow, and I can make this cow bigger, or I could make this cow smaller, or I could rotate the original image around, or I could put the image in a mirror and reflect it, or I could do a combination of these things, like make it bigger and reflected and rotated. However, all of these images that I have created so far are all similar to the original image because the images are proportional. What I mean by that is that as they've gotten X% taller, they've also gotten X% wider. So in that bigger image, if I made it twice as tall, I made it twice as wide, thereby keeping the proportions the same. For the smaller one, if I made it whatever, 1/3 as tall, I made it 1/3 as wide, keeping the proportions the same. And as long as the proportions are the same to that original image, they're similar. Now, that doesn't have to be the case. For example, I could have taken that original image and stretched it out wider, but not made it taller. So I changed the width without changing the height. Or I could do the opposite and change the height without changing the width. But in these two examples, you'll see that these are not similar because they are not proportional. The ratio of my height to my width is not the same as it was in the original image. So those two that are in red are not similar, while all the ones that are in green are because they are proportionate. The ratio of my height to my width has stayed the same. All right, let's do one more quick review about angles, because so far in this class we've learned 6 different ways that we can prove that angles are congruent. And we're going to need to use all 6 of these ways to be able to do these problems, so I wanted to review them. The 6 different ways that we have so far learned that angles can be shown to be congruent are: number 1, they could have the same measure shown. So for example, right there, I can see that angle M and angle B are congruent because they're both 53-degree angles. It says 53 right there. The same thing here, these are both 64-degree angles, so they must be congruent. They might not have the actual measure, but if they have the same markings, I know angles are congruent. So for example here, angle U and angle L are congruent because they each have one mark there, or one arc, or angle M and angle V are congruent because they both have 2 marks. They are the same markings, so they must be congruent. A third way that we know that angles can be congruent is if they are vertical, that is, they are across from each other. So for example, those 2 angles there are angle RNQ and angle MNL are congruent because they are vertical angles. A fourth way that the 2 angles within 2 different triangles may be congruent is if they are actually the exact same angle. So for example, right here, angle L, you see that this angle L is both in triangle LWV and triangle LNM. So angle L is similar to itself, or excuse me, is congruent to itself. The final 2 ways we know that angles are congruent are if we have parallel lines. If we have parallel lines with a transversal, then the alternate interior angles are congruent. So for example, in these triangles here, angle M and angle Q, we see that line LM and line RQ are parallel, and MQ is a transversal. So angle M and angle Q are parallel because they're alternate interior angles. Similarly, angle R and angle L would be congruent for the same reason. And then finally, if we have parallel lines, we can have corresponding angles. So for example, we see that in the third set of triangles over there, line MN and line VW are parallel, and therefore angle N and angle VWL are congruent because they are corresponding. For the exact same reason, angle M and angle WVL are also congruent because they are corresponding angles. All right, now we've done some review of angle reviews, we can get started with our actual notes here. All right, so the first reason why why triangles could be similar is if they have two angles that are congruent, and we call that angle-angle similarity. So if two angles in one triangle are congruent to two angles of another triangle, then the triangles are similar. Or so we see over here that angle S and angle M, the ones in blue, are congruent, and angle R and angle L, the ones are in red with double arcs, are congruent. If that's the case, then we see that these two triangles are similar, and we'd say that they're similar because of angle-angle similarity. Now, it's important that we write the corresponding points when we're writing a similarity statement. The similarity statement tells us which points correspond with each other. So we can see in this original triangle here that angle R and angle L, they're both in red, those are corresponding, so I happen to put them first. And angle S and angle M, which I put in blue, are corresponding, so I put them second. And then angle T and angle P don't have any colors associated with them. They're no markings, so they go together, so I put them third. Okay, now the order, first, second, third, doesn't matter. What matters is that the red goes with the red, the blue goes with the blue, and the black goes with the black. So I could have written the one I have here, the original one, but it would have been equally valid for me to write this one, or this one, or this one, or this one, or this one. In all 6 of these examples, you'll see that the corresponding points are in the same spot in the similarity statement. So the similarity statement lets me see that R and L are corresponding, S and M are corresponding, and T and P are corresponding. All right, let's do an example problem here. Our first objective was to determine if triangles are similar using angle-angle similarity, and if so, write a similarity statement. So here is an example problem number 1, and it's asking us to state whether these two triangles are similar. And so when we look at these, we can see that if the triangles are similar, then corresponding angles are congruent. And I see here that I put them in colors here so you can see angle ADU corresponds with angle ACB in purple. And so are those two angles congruent? Is the green angle congruent to the purple one? Well, when we do it, we see that the green one is 78, the purple one is 74, and therefore, of course, they are not the same because 78 does not equal 74. Therefore, they're not similar triangles. They're close, 78 is pretty close to 74, but no, they are not similar triangles. So what the similarity statement doesn't make any sense. Triangle ABC is not similar to any other triangle shown here, so I just wouldn't write that. All right, let's do another example problem, in this case example problem number 2. Before we do, let's do a very quick review to remind you that if a transversal crosses two parallel lines, then the corresponding angles are congruent. So in this case, we would say that A is congruent to E, and B is congruent to F, and C is congruent to G, and D is congruent to H. Using that, for this problem below, what we see here is that angle CBD and angle CAE are corresponding angles. They're in the same spot with those parallel lines. Similarly, those ones in red, angle BDC and angle AEC, are also corresponding, and they're congruent. Therefore, we can prove that triangle ACE is similar to triangle BCD. And again, notice that I'm matching up spots. So point A was in blue in the big triangle. So point B is in blue in the little triangle. They're in corresponding spots. Just like C is in the same spot for both. It's the same angle for both. And then that leaves D and E in red in the corresponding spots. And we know that these two triangles are similar using angle, angle similarity. And once again, it didn't have to be the particular similarity statement I wrote. It could have been that one, but it could just as easily have been this one, or this one, or this one, or this one, or this one. The key point is that the corresponding points are in corresponding spots in the similarity statement. Okay, we've done angle-angle similarity. Let's move on to side-angle-side similarity. So, if an angle of one triangle is congruent to the angle of a second triangle, and the sides that include the two angles are proportional, then the triangles are similar. So this is very similar to the side angle side we've done in the past for congruence, except for congruence, the sides had to be the measures had to be equal, they had to be congruent. Now the sides have to be proportional. So you can see here that in the example I'm showing over on the right, that angle A and angle Q are congruent, and that red side AB and the red side QR are in the exact same ratio as the blue sides, AC and QS. And so if that's the case, then we would know that triangle ABC is similar to triangle QRS for the reason of side angle side similarity. And once again, it doesn't have to be this exact similarity statement. It could be any of the 6 similarity statements as long as we're using corresponding points when writing the similarity statement. So it could have been the one I wrote, or this one, or this one, or this one, or this one, or this one. All of them are equally valid. All right, let's move on to our second objective for the day, which is to use side angle side to determine whether triangles are similar, and then if so, write a similarity statement. So we can do problem number 3. However, before we do, let's again do a very quick review to remind you that when two angles cross, they form vertical angles, and vertical angles are congruent. So in this case, angle A is congruent to angle D, and angle B is congruent to angle C. All right, now that we understand that, we can see down below here that angle SRT is congruent to angle KRT because they are vertical angles. So I already have the A in side angle side. I would just have to determine now, are the sides or the corresponding sides proportional? So let's do that. Okay, so once again, I've already proven that these are vertical angles, so these are congruent. And so now let's look. The bottom triangle I'll put in red. The top triangle I'll put in purple to make it easy to see. And if I want to do side angle side, I have to see if the corresponding sides are proportional. So to determine whether they are corresponding or not, what I'm going to do is I'll just use some shapes to help me figure it out. Now again, the shapes don't have any validity in and of themselves. You could use shapes, you could use colors, you could use letters, you can do anything you want as long as you are showing what side corresponds with what side. So I'm going to use a circle for the smaller sides. So the smaller side of the purple one is 21. I'm going to put a circle around that. And to make sure I correspond that to the appropriate smaller side of the purple one, I'll put a purple circle around the smaller side of that. And then the bigger of the two sides, I'll use a triangle. And so I'll use the red triangle here and a purple triangle here. Now again, the shapes themselves, circles, triangles, don't have any meaning other than the fact I'm just using the same one so that they match up. Now the question is, are they proportional? Are the ratios equal? So in other words, is the red circle over the purple circle, is that going to be equal to the red triangle over the purple triangle? Are they proportional? Are those ratios equal? Okay. Well, we could solve this two different ways. The first way we could do it, so we're trying to figure out is this the case? Okay. So the two different ways we could solve it. The first way we could solve it is to reduce the two various fractions. 21 over 35, if I divide that by 7 over 7, I get that that's equal to the ratio of 3 to 5, or 3/5. 30 over 50, if I divide by 10 over 10, I see that that is equal to the ratio of 3/5, or the fraction 3 over 5. Is 3/5 equal to 3/5? Yes, of course it is. And so, yes, we know that these two ratios are proportional. All right, the other way I could do it, if I didn't want to do simplification of fractions, is I could use my cross multiplication. Is 21 times 50, is that going to be equal to 30 times 35? Well, so is 21 times 50 equal to 35 times 30? Well, 21 times 50 is equal to 1,050. 35 times 30 is equal to 1,050. So yes, 1,050 is equal to 1,050. So yes, that also shows that these are proportional. So now that I know that they're proportional, I can prove that triangle SRT is similar to triangle KRL using SAS, or side angle side similarity. And once again, it didn't have to be that similarity statement. As long as the corresponding points match up, that would be appropriate. So it could have been, so again, I have the S is across from my triangle. That goes with K, which is across from my red triangle. I have T, which is across from my purple circle. That matches up with L, which is across from my red circle, so I know that these are in the same, these are corresponding points. But again, it didn't have to be this one. It could have been this one, or 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 this one. In all 6 of these cases, the corresponding vertices of the triangles match up in the same place in the similarity statement. All right, so we've now done angle-angle similarity and side-angle-side similarity. So the final reason to prove triangles similar is side-side-side similarity. And that says that if the corresponding sides of two triangles are proportional, then the triangles are similar. So in the example over here, I have that the ratio of the red sides, AB to QR, is equal to the ratio of the blue sides, AC to QS, is equal to the ratio of the purple sides, BC to RS. If that's the case, then the triangles are congruent. And they'd be congruent by side, side, side. And again, once again, you can use any of these 6 examples so long as the corresponding vertices of the triangle are in corresponding places in the similarity statement. All right, let's look at our third objective, which is to use side-side-side similarity to determine whether two triangles are similar, and if so, write a similarity statement. Okay, let's look at example problem number 4 here. All right, so for example problem number 4, once again, I have to make sure that I'm matching up the appropriate sides. So I'm going to use shapes again. Again, doesn't have to be shapes. The shapes don't have any meaning in and of themselves other than to just make sure that I'm not going to make a mistake and match up the appropriate sides. So I have a purple triangle and a red triangle. For the smallest side, I will use circles. So 8 is the smallest side of the purple triangle. That's going to correspond to 20 of the red triangle because that's the smallest side. For the middle side, I'll use the shape of a triangle. Again, I could have used anything. I'm just using a triangle. And so that 10 must correspond to the 25. And then finally, for the third side, for that 12, I'll use a square. So I know that 12 must correspond to the 30. And again, the shapes themselves don't have any meaning. It just allows me to see that I know that if these are going to be similar triangles, then the small side of the purple ratio to the small side of the red one must equal the medium side of the purple one over the medium side of the red one, which must also equal the large side of the purple one over the large side of the red one. So to determine whether this is the case, again, I can do one of two different ways of doing it. The first is I can just simplify the various fractions. So 8/20ths, if I divide by 4 on the numerator and the denominator, I get 2/5. 10/25ths, if I divide by 5 in the numerator and the denominator, I get 2/5. And for 12/30ths, if I divide by 6 on the numerator and the denominator, I get 2/5. And 2/5 is equal to 2/5 is equal to 2/5. Is that the case? Yes, of course it is. So I would know that these three sides are similar, and therefore these three sides are proportional, therefore the triangles are similar. And therefore I would say that triangle SGH is similar to triangle SRQ using side-side-side similarity. And again, I want to match up the sides. So S is across from the square, S is across from the square, G is across from the circle, R is across from the circle, H is across from the triangle, Q is across from the triangle. So I know I've matched up these sides appropriately. The corresponding sides our corresponding vertices are matched up, but so that I could do it that way. Another way I could do this problem is instead of doing the fractions, I could use cross multiplication and just do cross multiplication multiple times. So I could say, is it true that the ratio of the first two, the first two ratios proportional? And I can do that using cross multiplication. So is 8 times 25 equal to 20 times 30? Is that 200 equals 200? Yes, that's true. And then I can do the same thing for the second and third ratios. So using 10 and 30, cross multiplying that with 12 and 25, is it the case that 10 times 30 equals 25 times 12? And that would be 300 equals 300. So yes, both of those is true. Both of those are true. So I could then say, therefore, I know that those triangles are similar through side, side, side. And once again, I want to match them up, making sure that I'm choosing the appropriate corresponding vertices, and indeed I have. So that would be correct, but it doesn't have to be that one. It's equally valid to use this one, or this one, or this one, or this one, or this one. All of those are equally valid because the corresponding sides match up in the similarity statement. All right, for the remainder of class, I'd like for you to do IXL similarity rules for triangles, and the code for that is XJQ.